And for our next speaker, we have Marieke van Beest from Oxford, and she'll tell us about holography, one-form symmetries, and confinement.
Yes, precisely. Thank you very much. I'm very happy to be here, so thanks a lot for inviting me. So I'm going to be telling you about some work that appeared earlier this year that I did in collaboration with Fabio Prozzi, Dawi Gold, and Sakura Shea-Funomichi. And like Marieke said, this is about holography, one-form symmetries, and confinement. And the main motivation for this work was that we wanted to access a strong coupling regime of QFTs, and we wanted to do it by using a combination of string theory methods and higher form symmetries. So in particular, what we set out to do was we wanted to develop new holographic methods to compute anomalies of discrete higher form symmetries and to derive the topological quantum field theory sectors that match these anomalies. And we wanted to do it in a way that didn't rely on an anomaly matching argument or even a UV Lagrangian. And so this paper that I'm going to talk to you about is in essence a proof of concept for the case of confinement in 4D n=1 Superyoung mills. Okay, so first a bit about generalized global symmetries, and this is going to be a lightning review. So I'm sorry if it doesn't quite cover the topic. But in essence, generalized global symmetries and their TOFT anomalies can highly constrain the dynamics of gauge theories. And that's why they're so useful. So a Q-form symmetry G in D dimensions can be characterized as follows. So we have a set of topological generators of the symmetry that are the charge operators, these UG, and they're defined on D minus Q minus one dimensional manifolds. And they generate a symmetry transformation that's this element in G. They link the charged operators, which we call V, and they live on Q dimensional manifolds. So an equivalent way to this, to describe a Q-form symmetry is to couple the theory that has this Q-form symmetry to a flat background gauge field. And the reason why it has to be flat is in order to preserve this topological quality. And this gauge field will be a Q+1 form for a Q-form symmetry. Then the symmetry generators are implemented by a G holonomy in this background field. So in the case of the one-form symmetry, which is the one we're going to be mostly interested in, what this looks like is in 4D, we have the symmetry generators are these topological surface operators, and they act on line operators such as the Wilson lines. The one-form symmetry also provides a diagnostic of confinement. And the way this works is because the order parameter for the one-form symmetry is the VEF of the Wilson line. And that obeys an area law in a confining vacuum. So that means that the one-form symmetry is conserved. And conversely, if we have a broken one-form symmetry, that implies that the vacuum is deconfining. Okay, so how do higher form symmetries appear in holography? And in order to try to explain the ideas behind this, I want you to just consider the case of AdS5 times S5 with n units of F5 lux through the internal space. And the dual of that is, of course, n=4 Superyoung mills. Okay, so the idea can be seen by considering the Chern-Simons term in the type 2B action, and then reducing that on the internal space in order to gain a 5D effective action for the fluctuations B and C of these fields around the background. And the result of that is this topological action. And what that action implies is that both this B and C field are in fact flat set n gauge fields. So because they're flat set n gauge fields, we can construct topological surface operators that live in the bulk, like this. However, these surface operators are not mutually local, meaning that if I exchange the two, I pick up a phase which is proportional to their linking number. So in order to pick out a maximal set of mutually local line operators in 4D, what we need to do is impose boundary conditions on this B and C field. So the NS and Ramon 2 form. And I'm going to be discussing just one example, which is imposing Dirichlet on the B field and Neumann on the C field. And in that case, what we find is that the 4D Wilson lines will be furnished by this UB operator, where the surface that it lives on in the bulk has a boundary in the boundary of ADS5. So like this. And then in turn, the symmetry generators will then be given by this UC operator on a closed manifold. And that realizes the SUN gauge group in the 4D field theory. We could also have switched so that the boundary conditions are the other way around. And in that case, we would have gotten TOFT lines in the dual field theory instead of Wilson lines, and then realizing the PSUN gauge group. Okay. But in the case of these Wilson lines, they also are screened, and we can see that from integrating the Bianchi identity, which tells us that n fundamental strings can end on a so-called baryon vertex, which is a D5 wrapping the S5. And because they can end there in the bulk, that corresponds to the 4D Wilson lines being screened, and thereby we generate the one-form symmetry, which is set n, because we can have the Wilson line to the n power until it becomes trivial. Okay, but what we're interested in is describing the holographic dual of confinement and studying the properties of this theory. So one of the most successful holographic realizations of n=1 super Yang-Mills is the Klebanov-Strassler solution in type 2b supergravity. And that is constructed from two main ingredients, the first being a stack of n D3 branes probing the conifold, where the conifold is this cone over T11. And the important thing for our applications is that the T11 is topologically a 2-sphere times a 3-sphere. Now, the second main ingredient is a stack of MD5 branes that are wrapping the S2 inside the T11. Those are also called fractional D3 branes, and importantly, they break conformal invariance. They also make sure that the S3 doesn't collapse at the origin because of the flux through it, thus deforming the conifold. So the metric of the entire space is given here, and we see that here we have the T11, and then we have this external part that we call M5, and we're interested in studying the bulk theory that lives here. Compared to the conventional ADS case, we can see here that the radius has picked up a log dependence on the radial direction. And that has a singularity, which ultimately depends on this R0, which is a UV scale. Okay, so since we've broken conformal invariance, that means that the dual field theory has a non-trivial RG flow to it. And an RG flow is dual in the bulk to the radial direction. So what that means is we can start very far away from the center of the bulk at this scale R0, and then that will be dual to the UV of the field theory. Then as we move inwards towards the origin of the bulk in the radial direction, that corresponds to flowing to lower energies in the field theory. Okay, so because of this stack of fractional D3 branes, the flux through the T11, the F5 flux through the T11 also picks up this log dependence. And what that means is that the effective number of D3 branes is in fact only integral at some very specific slices, so at these specific values of the radial coordinate. And it's only at these specific slices where the number of D3 branes is integral that we have a good interpretation for the gauge theory dual. So what happens as we start out at R0 in the bulk and then move inwards towards the origin along these RK slices is that the dual field theory realizes a Seiberg duality cascade. And the Seiberg duality cascade is as follows. So we start out in the UV with an SUN plus M times SUN gauge group. And then as we flow towards lower energies, this group becomes strongly coupled. And once that happens, we can perform a Seiberg duality transformation to get to a new gauge theory description, which is this SUN times SUN minus M. So we're reducing the gauge groups, the ranks of the gauge groups. And flowing to lower and lower energies, we can keep doing this until finally we end up with SUM, super Yang-Mills. And if we flow further, we find the confinement. Okay, so we're going to be studying the IR phase of n equals 1 super-Young mills. So what should our expectations be? What do we expect to find here? So first of all, we expect to find an unbroken one-form symmetry because we know that the vacuum of this theory have confinement. We also know that this theory exhibits chiral symmetry breaking, which means that starting from a U1 R symmetry, the ABJ anomaly will break it down to Z2M, and then it will be further broken by chiral symmetry breaking all the way down to Z2. And then in the far IR, we know that this field theory should be described by a TQFT. So we would like to derive all these properties holographically and using higher form symmetries. And first, we start by determining the one form symmetry from the bulk. And the way we did that was by reducing the equations of motion for the two form fluctuations of type 2b on the internal space, and then lifting them back up to a 5D bulk action. And the result is the topological action given here, where now the B2 field is still just sourced by fundamental strings, whereas the C2 field is a bound state of D1 and D3 branes, where the D3s are wrapping the S2. And the 5D equations of motion that we find are given here. And what they imply is that both the B field and the C field are flat set GCD and an M gauge fields. And now you can probably see the story repeating itself. So what we want to do with these flat set GCD and an M gauge fields is we want to construct topological surface operators from them. So in precisely the same way, analogously as we did with the ADS5 process 5 case, we construct these topological surface operators. And again, these won't be mutually local, but we can find the line operators in the 4D field theory by letting one of the surfaces end on the boundary. And then the other one will be the charge operators. So in this case, again, if we impose Dirichlet on the B field and Neumann on the C field, we find that the surface charge operators are given by this UC operator on a closed manifold. And this acts on charged 4D Wilson lines furnished by these UB operators. And in this case, they have a boundary that ends on one of these RK slices. So rather than having the string world sheets end all the way out at the boundary of ADS5, we now have that they have a boundary at each of these RK slices. Again, we can consider the screening of these lines by integrating the Bianchi identities, which then tell us that wrapping a D5 on the T11 will screen n minus km fundamental strings, whereas wrapping a D3 on the S3 will screen m fundamental strings. And then the minimal configuration of screen strings will be precisely this greatest common divisor of n and m. And thereby we generate the one form symmetry along the entire RG flow, which is the set GCD of n and m. Okay, so far so good. So we've determined the one form symmetry in the dual field theory. And now in order to be able to study chiral symmetry breaking, we first need to study or to determine the R symmetry dual. And the dual to the U1 R symmetry turns out to be the read vector of this T11. So this is the gauge field that's associated to the U1 isometry of this internal space. And fortunately, the 5D couplings of this gauge field have already been determined, and we use this consistent truncation of Cansani and Fado, where they find, well, these are the relevant terms that they find in their consistent truncation. So here we have also specialized to the case where n is a multiple of m, and that is in order to flow to the SUM in the IR. We could also have something different, like rather than being a multiple, we could have had there was a multiple plus 1. In this case, we would have flown to SUM plus 1, and that's also fine, but it's not the case we're interested in. Okay, so the first term that we have here in blue is the kinetic term of the axion. And what that is doing is it's implementing a Stuckelberg mechanism for this U1R gauge field. So to see that, we can use the symmetry of the action to completely gauge away the axion, which then gives rise to a mass term for this U1R gauge field. So having fixed the axion to 0, we still have a residual discrete symmetry, which is generated by all the alphas that sit inside 2 pi over 2m set. And this is a direct way to holographically realize the ABJ anomaly. So we can see that here we have the breaking of the U1R down to the set 2m. Right. So having fixed the axion to be 0, we also still have this term here on the right, which is the b squared a term. And that is a mixed TOFT anomaly between the set 2m 0 form background A and the set M one form symmetry background. So before, the one form symmetry was the set GCD of n and m, but because we specialize to the case where n is a multiple of m, now we just have a set M one form symmetry. So it was shown recently by Cordova and Omori that for there to be able to exist a TQFT in the IR which saturates this anomaly, the anomaly itself must be integral. So together with requiring that this anomaly is integral, and the fact that we know that there should be an unbroken set M one form symmetry in the confining vacuum, that in fact implies that the periods of this gauge field must be half integral. And then that realizes the chiral symmetry breaking from set M all the way down to set 2. And in the symmetry breaking, we generate M vacua, and those are separated by domain walls of D5s wrapping the S3. Okay, so we were happy with having identified the symmetry breaking pattern, but afterwards we were quite surprised and excited to see that not only could we do that, we could also find an imprint of the IR TQFT directly in the supergravity. So the way to see that was to consider the 5D bulk action in the IR, and that looks like this. So here the relevant degrees of freedom are again this axion and the B2 field, which couples to the fundamental string. And then finally, there's this 3-form gauge field, which is in the bulk, it's the Hodge dual of the axion. So the last term here implies the equation of motion on the deformed conifold. So in the IR, where we're sensitive to deformation, the equation of motion is this single one. And once that has been imposed, this action gives rise to topological counterterms for the boundary TQFT. So introducing this field phi and evaluating this action at the boundary, we find this expression for the 4D TQFT. And here the M vacua are realized as being labeled by the VEF of this phi field. And they're separated by domain walls, which are given by this 3-form gauge field. Now, this action agrees with the proposal by Gaiotto, Kapustin, Seiberg, and Willett, which was based on an anomaly matching argument, but our derivation does not rely on that. A final comment I want to make is that the supergravity gauge transformations in fact signal the presence of a 3 group, since the 1-form symmetry background enters the shift of the 3-form gauge field here. We can also see that that's the case by considering gauge invariance of the world volume action on the D5 domain walls. And they extend into the 4D spacetime in precisely such a way as to produce this combination of fields that we saw in the 4D TQFT. Okay, so a few conclusions is we focused on the holographic dual to the Seiberg duality cascade, which flows to n equals 4 super-Young Mills, 4D n equals 1 super-Young Mills in the IR. And from the bulk, we derive the 1-form symmetry along the entire RG flow by constructing topological surface operators and imposing boundary conditions on these operators. Then we identified a Stuckelberg mechanism and a mixed 0-1 form symmetry anomaly, which was responsible for the symmetry breaking of the R symmetry. And finally, we gave an independent derivation from holography of the TQFT that governs the confining phase. One more remark that I want to make is we also looked at the S-dual realization of n equals 1 super-Young Mills, which is the Maldacena-Nunez solution. And here the anomaly, so the mixed 0-1 form symmetry anomaly, can also be derived from the anomaly polynomial of the little string theory. And that's also in the paper. Finally, I started out by saying that this paper is proof of concept, and indeed there's a more general method that lies underneath it, and where the idea is to use supergravity couplings to derive anomalies and IR sectors of quantum field theories. And this idea has lots of applications where topological couplings are determined at the boundary of the compactification space. So, for example, you could consider other interesting holographic setups, such as if we're thinking about pheno applications, you could consider non-SUSY deformations, where the Klebanov-Strasser solution has also played a big role. Another possibility is to think about finite temperature of phase transitions, for example, something like the Hawking-Page phase transition. And in this case, rather than having the non-trivial topology of the internal space give rise to some interesting higher form symmetries and anomalies, we could study here the topology of the external space, which will be an S1 times an S3 because of the compactification of the time circle. And that could potentially give rise to interesting higher form symmetries as well. Another application is we could move completely away from these holographic setups and into the realm of geometric engineering. So for example, one thing that we've been thinking about is considering the M-theory realization of n equals 1 Sobering Mills, which is M-theory on this G2 manifold. And there it's been shown by Morrison, Schaefer, Marieke, and Willett that the one-form symmetry can be computed by the link, from the link. And then the question is, can we derive the anomaly and the TQ of T from this description also? Okay, so I think that's all I wanted to say. I'm not sure how I'm doing on time. I think it was probably
excellent.
pretty quick, no?
It was excellent.
Cool.
You've got a lot of time left, like 5 minutes left.
That's great.
Okay, let's thank Marieke for the excellent talk. And is there any other question? Yes, Ling and Craig. Ling?
Hi, Marieke. Thanks for the great talk. So I wanted to ask again about this three-group symmetry that you have in the bulk. Could you, is that just the, or could you explain how this three-group in the bulk manifests, or to what it is related on the in the boundary theory or in the holographic dual field theory?
Right. Okay, so in the bulk, these are gauge transformations, right? So the three group would be in the dual field theory, where you have the one form symmetry background mixing with this with the three form. And actually, this three group interpretation was shown by these people. So, just to be fair. And then the point is that well, okay, so the point is that these higher groups appear when you have a mixing of these symmetry transformations. And just thinking, I guess this would be a background for a two-form symmetry then. But I can't remember exactly what this two-form symmetry is. I'm sorry.
No problem. No, I was just wondering. So the equation that you have here, right? These are so the B and the C's, they are supergravity fields. So this is in the
That's right.
In the 5D setting. You have this three group. But so
it
my question is
because of the boundary conditions that we impose.
So it persists as the higher group structure in the field theory.
Yes.
I see. Okay.
Precisely.
Okay. And sorry, may I just ask another question? The U1R symmetry, naively, you would. Does that have also its associated one form U1 symmetry? And presumably then when you break it, also that gets broken to some discrete one form symmetry? Or is there some other argument that it's completely broken to begin with?
So which one form symmetry of the R symmetry would that be? Okay, so the R symmetry is clearly a zero form symmetry, right? So how would that be associated to a one form symmetry?
Well, I mean, if you have a zero form, okay, if you have a zero form U1 gauge symmetry, then you have also a one form global symmetry, right? From now just basically line.
Right. So, but so the U1, right? So the gauge field is the supergravity you want, right?
Right.
But in the field theory, that's a global symmetry.
Okay. Okay.
So,
Good. All right.
yeah.
All right. Thanks.
Right, Craig.
Hi. So I might be revealing that my information is a little bit out of date here, but you wrote down, or you said that you used the anomaly polynomial for the little string theories. But
Yes.
so if I'm remembering correctly, I thought that this was not something which was known how to compute because you don't have the cancellation of the anomalies to constrain the coefficients in the Green-Schwarz term. So yeah, has that changed? Has the story involving the higher form symmetry allowing us to compute the anomaly for the little string theories now?
Let me think. So I think so in principle, this n equals 1 Soubian-Mills is realized on these in this S-dual frame on NS5 branes, right? And then so that's a 60 theory. So actually, I think we're working with this 60 polynomial. And then you're saying, what is the problem with it?
Good. So the problem is that the 60 anomaly polynomial contains a term, for example, which is like C2R squared.
Yeah.
So in the superconformal field theory context, the coefficient of this term is basically fixed by demanding that the theory has no gauge anomalies or mixed gauge anomalies. But in the little string context, you can't make that assumption that there are no anomalies, and so I don't know any way to fix this coefficient.
Okay, I'll have to get back to you on that. I can't remember right now.
I see. Yeah.
I mean,
just curious.
I'm sure it's explained in the. It's very explicit in the paper, but I'll just have to get back to you.
Yeah,
to be able to discuss
I will
that
take a
again.
look. Thank you.
Yeah. Thanks. Sorry.
All right. Is there any other question? If not, let's thank Marieke again for the excellent talk, and then let's see you next week. Thanks a lot.
Thank you.